Hi, this video is going to show an example problem from Chapter 2, Average Acceleration. Since we're just getting started here with solving problems in physics, I want to show you this general problem solving steps, which is a general set of steps which could be used for any type of physics problem, and we're going to apply them here. You should take a moment to look at these steps and be familiar with these, and we'll go ahead and use them in this problem, practice these, and use these in all the problems you solve in physics. So we're going to look at this problem in particular. Let's go ahead and read it first, and remember we're trying to gather information here, visualize this problem. We may need to read it several times. After attaining a top velocity of plus 120 meters per second, a rocket car driver releases his parachute and hits the brakes at t0 equals 8 seconds. At t final equals 15 seconds, the car is slowed to a velocity of plus 30 meters per second. What was the car's average acceleration? Well, in this problem, it kind of tells us what we're looking to solve for here, right in the last question. What was the car's average acceleration? That should be a clue for you to go look up the definition of average acceleration, and this is what it is. The average acceleration is equal to the change in velocity divided by the change in time. And we've got a bunch of numbers here in the problem. Where do these belong? Well, I'm going to go ahead and draw a picture of this to try to help understand a little better where those numbers go. So you can see the car, it's moving along from the left to the right, and you can see the velocity vectors here. As they proceed on, they get shorter and shorter, which means the car is still going to the right, but it's slowing down. Whereas the acceleration points in the opposite direction, towards the negative direction, towards the left. Well, we can always plot motion in one-dimensional along a line, a single axis. And so let me go ahead and draw an x-axis here. Here's the positive direction. And I'm going to say this is where we start the motion. This is where x initial is at. And this is also where we start the clock here. T initial, in this case, it's equal to 8 seconds. What's the velocity at the beginning? V initial. Well, it attains a top speed of plus 120 meters per second, and we're going to go ahead and use that at the beginning of this at 8 seconds when we start, so that's going to be plus 120. In fact, if it's a positive number, I don't really need to write the plus sign. I only need to write it for if it's going in the opposite direction, negative. So we got 120 meters per second initially towards the right, positive. Now, afterwards, it says the car is at t equals 15 seconds, the car is slowed to a speed of 30 meters per second. Well, let's say that's over here at the end here. So we've got our final position here, and at the end, this is a time 15 seconds. Do we know what the velocity is here? We do know what it is, v final. It's given to us, and it is equal to 30 meters per second, positive. All right, so we've identified, notice that in solving this type of problem, we don't really care about what's going on in the middle of the axis. We only can look at the two endpoints, the start and end of the motion. And so with this data, we can go ahead and figure out what delta V and delta T are. You might also be wondering what delta X is. We don't actually need it in this problem. If we want, we could have gone ahead and just called this starting position here 0. We're free to choose what we want here. So we could say x initial equals 0 if we want, but we don't need that information. Let's figure out what delta V is. So to rewrite this equation here in another way, remember delta means V final minus V initial. And delta T means T final minus T initial. So we can plug these numbers in since we know all 4 of these. What's V final? There it is, 30 meters per second, and V initial, there it is. From the equation, it's minus, and then we've got 120 meters per second for V initial. Divide that by T final, Looks like I had a typo here, right? That should be t final. And we've got 15 seconds minus, what was t initial? There it is, 8 seconds. So we'll see that elapsed time comes out to just 7 seconds in the bottom there. And the change in the velocity, 30 minus 120 meters per second, gives us a minus 90 meters per second. Putting this into the calculator, we find out that this is equal to negative 13 meters per second squared. Now let's check this out and see if it makes sense. We've kind of gone through the various parts of this, right? Here we've looked at this whole area, we've kind of visualized the problem. Here we've figured out how to strategize this. Here we've gone and done the math, we've solved it. Now we need to check if we're right here. Are the units correct for acceleration? They are, meters per second squared. How does that come out? Well, let's look and see. A meter per second divided by second. What's that? I can divide the bottom second by 1. And if I go ahead and take the numerator, I can multiply by the reciprocal of the denominator, and then that ends up giving us meters per second squared, so that's good. Now let's look at the sign. It's a negative sign. That means that the acceleration points towards the left. Does that make sense? Well, look at the velocity. Here it's big. Here it's small. So the velocity is positive. It's moving to the right, but it's getting smaller. It's decreasing. Anytime the speed decreases, that means that the acceleration is opposite the direction of the velocity. And that's the case we have here. Since the velocity is positive, the acceleration in this case is negative. And so this makes sense. In fact, as a general rule, let's move this where we can see it a little bit here. We can always say this. Anytime that the velocity and the acceleration have opposite directions, the object is said to be slow. The object slows down and is said to be decelerating. So we've checked this out, and everything looks good. We are satisfied with our answer here.